So let's take a look here at example number 1. I'm actually going to see here that this is an exact copy of the opening motivation problem for this section. That is, it's going to be the problem that's dealing with exactly the same region that we started with that looked something like this. And we were interested in rotating this region around the y-axis. Okay, so I'm going to go ahead and try to figure out how I would do this, because we saw in the motivation that it was very difficult to do this with the washer method. So let's see how we could use this concept of cylindrical shells in order to be able to set this up. Now, to imagine cylindrical shells, I'm not going to actually go ahead and draw the full 3D figure. That's going to be one major difference in this section compared to previous sections. Instead of drawing the entire figure in the duplicate, the mirror image on the other side of this rotation axis, I'm instead just going to start with how the shells were created in the work that we did up above. Remember that I started with an individual rectangle and I imagined rotating it around my axis. So here, I'm going to start with a red rectangle. Okay, I'm going to start with this. Now you could position your rectangle anywhere inside of your region, anywhere at all. This rectangle right now, I'm just going to position here. I don't even know what x-coordinate it's at. Let's just suppose it's at x-coordinate x. Based on my original picture, I know that x-coordinate was somewhere between 0 and 2. Okay? I don't know where it is, though. You could have drawn yours a little bit further to the left, a little bit further to the right. It doesn't really matter. Now, if I imagine rotating this rectangle around, and notice I've made this a very skinny rectangle, I could imagine that that would probably land somewhere over here, and then I'll connect the dots in the same way that I've normally done in the previous sections. Except here, I'll see that what I'm creating is the shape of one of my cylindrical shells. This is it. This is actually as much as I need to draw at this moment in time. What I'll do now is I'll just go ahead and label a couple things. I'll see that this side over here would represent the height of my shell. And of course, I can draw my radius in here. This would measure my radius of that shell. If I can find those things, then notice I have everything I need to go ahead and set up my resulting integral. So I'll go ahead and start by just recording the lengths of these different pieces. So I'll say, we see that our shells, I'll start by saying expand horizontally, and so we have a dx problem to work with. Again, imagine that if I wrapped more and more shells around this, they would add thickness to this overall picture. Another way to think about this is that I had to place my individual starting rectangles kind of in a vertical motion here like we did, and that they could have stacked left to right of each other, not top and bottom. So I know this is going to be a dx problem, so that means I want to measure my height and my radius in terms of x-coordinates. So let's start by observing that our height is pretty easy to find. I would just need to know the location or the height of this dot on the top, that is its y value, and this value down at the bottom. Well, the y value at the bottom is clearly going to be 0, but the y value at the top changes every time I draw a new starting rectangle. In fact, this time it's determined by the function y equals 2x squared minus x cubed. So instead of stating y minus 0, I'll state 2x squared minus x cubed minus 0. Of course, you don't have to write the minus 0 if you don't want to. We'll also be able to see here that there's an easy formula for the length of this r. Again, I want to communicate it in terms of x-coordinates. But what I can already see is that I can tell that my starting rectangle was drawn at this coordinate of x. And so if I want to find the length of this in x-coordinates, well, the x-coordinate on the right side, I guess, is just a mystery x. And the x-coordinate on the left side is clearly 0. So the distance there is x minus 0. Again, you don't have to write the 0. But this then becomes super easy to then write my integral. The volume then of this would be 2 pi times my radius, which I'll just simplify down to x, multiplied by my height, which I'll just simplify down to this. I'm going to put my dx on to add that thickness, and then I just have to consider my bounds. My bounds again are going to be where are all the spots where I could have drawn that starting rectangle. And so the furthest left I could have gone would have been 0, and the furthest to the right that I could have gone would have been at 2. So this here is an integral that should find the volume of the resulting solid. And again, in these videos, I'm not going to go ahead and evaluate these. I'm going to leave that as something for you to try on your own, but if you did attempt this one, you should be able to confirm that you get down to an answer of 16 pi over 5. In the next video, we'll do a little bit of a compare and contrast between this shell method and the old washer and discs methods to understand how they're related and when I might be able to choose or understand when to choose which one I'm interested in working with.